Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about MESC-RCNN published on ICCV in 2017. MESC-RCNN is an extension of FASTER-RCNN, which is a well-known object detector. Currently, MESC-RCNN has been widely used for instance segmentation. The outline of this lecture includes introduction about what instance segmentation is and how the MESC-RCNN works. Next, we introduce the two main parts of the MESC-RCNN, namely ROI-align and the MESC branch. ROI-align about the objective, formal statement, and align steps. MESC branch about design concept, network architecture, and MESC laws defined for training. Instance segmentation is a combination of object detection and semantic segmentation. Object detection refers to localize all object instances by bounding buses and assign class labels to all object instances. Semantic segmentation refers to produce the masks of all object instances. Formally, the inputs of the instance segmentation are an image I and the set of object classes to be detected and segmented. For this image as an example, the object classes to be detected and segmented are cat, dog, and duck. The output of the instance segmentation are bounding buses R1 to Rk of the k detected objects. Their class labels L1 to Lk, and their masks M1 to Mk respectively. What is MESC-RCNN? MESC-RCNN is an extension of FASTER-RCNN published on IEEE Transactions on PAMI in 2017. MESC-RCNN improves the FASTER-RCNN in two aspects and is used for instance segmentation. It adds a branch for predicting a segmentation mask to each region of interest. And it proposes ROI-align to replace ROI-pooling for preserving exact spatial locations. We firstly described the processing flow of the FASTER-RCNN, which consists of two stages, including proposal generation and detection. For an input image, the FASTER-RCNN firstly computes its convolutional feature map. Any existing convolutional neural networks can be used for this purpose, such as VGG16 residual network. During proposal generation stage, a region proposal network RPN is used for generating a set of object candidates called object proposals. During detection stage, ROI-pooling crops and normalizes the feature maps from the convolutional feature map for the first proposal, second proposal, to the last proposal. Finally, detection network, including regression and classification branches, predicts parameters for localizing all objects and determine their class labels respectively. The video about the detail of FASTER-RCNN can be found in YouTube via this link or our website gg.gg/quarter. As mentioned before, masked RCNN improves the faster RCNN in two aspects. Firstly, it directly adds a mask branch for predicting object mask. Secondly, it replaces ROI pooling by the proposed ROI align for preserving exact spatial locations to improve the segmentation accuracy. For ROI align, its objective is to extract features within all ROIs for further parameter prediction. More specifically, it crops the feature maps within the ROIs and then normalizes the clipped feature maps to the fixed size and small ones. ROI align extracts feature maps by interpolation instead of quantization in ROI pooling. This preserves exact spatial locations and improves mask accuracy about 10% to 50%. You can find a discussion about ROI pooling as well as ROI align in our YouTube videos or via our website. Formally, one input of ROI align is the convolutional feature map of the input image from a deep convolutional neural network. In this work, the backbone used is residual network published in 2016. The output from the final convolutional layer of the first stage is used as the input of ROI align. For an RGB color image with size 406 times 300, residual network scales down the image with the factor equal to 1/16, and thus result in a convolutional feature map with the size 25 times 18 times 256. The next input to ROI align is a list of object proposals from RPN. AV ROI is a rectangular bounding box and described by the coordinates of top left and right bottom columns. This example shows 3 ROIs from RPN and the coordinates of their top left and right bottom columns. Refer to our RPN video on YouTube. You can find the detailed explanation of RPN. The output of ROI align are the ROI feature maps that are normalized to the fixed size k by k by c. K is the predefined size, and C is the number of channels of input convolutional feature map. In this paper, K is set as 7 for producing ROI feature map with the size 7 by 7 by 256 for regression and classification branches. To make segmentation accurate, K is set as 14 for the mask branch. ROI align consists of 4 steps. The first step, ROI mapping, directly multiplies the scaling factor to map ROI to convolutional feature map instead of using quantization in ROI pooling. The second step, ROI division, directly divides the width and height of the mapped ROI by K to have K by K grids without quantization in ROI pooling. The interpolation step interpolates the values of all sampling points. Finally, the max pruning step finds the maxima of all S by S sample points in a grid to output the ROI feature map with the size K by K by C. In the ROI mapping step, it maps the ROI to convolutional feature map by directly multiplying the scaling factor without quantization. Since the scaling factor is 1/16 in this work, the corners of ROI after mapping is 7.0, 2.8, 13.7, 13.3. At division step, it directly divides the ROI with the height by K without quantization. For explanation purpose, we use K equal to 3 here. After division, we have the width and height of a grid respectively about 2.2 and 3.5. At interpolation step, we firstly divide the grids into S by S cells, and S is set as 2 in the original paper. Then we take the centroids of the cells as sampling points. The coordinates of the sampling points can be computed by using simple equations. For example, the coordinate of the green sampling point can be computed as these two equations. That is the coordinate of the starting point plus the displacement. The displacement is the cell size times the distance from the starting point in the unit of cell size. Then, we interpolate the feature values of all sampling points by the operation called bilinear interpolation. For example, by using bilinear interpolation, we can compute the feature value of the green sampling point. The details of bilinear interpolation can be found in our YouTube video, namely ROI pruning and the align. The final step, max pruning of ROI align, is to process every channel independently and take the maxima of all sampling points in a grid as the response. Take the maxima of the first grid, second grid, until the K by K grid. By aggregating all maps, we can obtain the normalized ROI feature map. Next, we introduce the proposed mask branch used in mask RCNN. Before detailing the mask branch, we introduce the three main design concepts of the mask RCNN. Mask RCNN follows the spirit of the faster RCNN that simplifies the multi-stage pipeline. That is, it predicts the object mask in parallel with classification and regression branches, but not in cascade manner that will increase the pipeline stages. For accuracy consideration, mask RCNN maintains object spatial layout without collapsing it into a vector representation. It uses fully convolutional network for mask prediction. Instead of flattening ROI feature map into a vector representation and predicting mask by fully connected layer. binary. Mask RCNN decouples the mask and classification predictions. It predicts a binary mask for each class dependently. This makes the network to generate masks for every class without competition among classes. In this example, the mask branch outputs the class map with 3 channels, which denotes the 3 masks, respectively for cat, dog, and duck, but not a single channel class map, whose point value denotes class label. This is the key for good instance segmentation results. As mentioned before, in mask RCNN, the ROI align outputs a feature map with size 14 by 14 by 256 to the mask branch. The architecture of the mask branch is composed of 2 steps: a stack of 4 consecutive convolution processes and a deconvolution process. The output of the mask branch is a 20A by 20A by C feature map, where C is the number of classes. See the input feature map in the front view. The convolution step firstly packs 1 pixel around the feature map. Then 256 convolutional kernels with the size 3 by 3 by 256 are used for convolution. Convolution by 1 kernel results in a 14 by 14 by 1 feature map. Convolution by 2 kernels results in a 14 by 14 by 2 feature map. Accordingly, the output of the convolution operation is a 14 by 14 by 256 feature map, the same as the input one. This operation is repeated for 4 times, and finally results in a 14 by 14 by 256 feature map. At the deconvolution step, it firstly inserts 1 0 point between input points to enlarge the feature map from 14 by 14 to 27 by 27. Then it packs 1 pixel around the feature map and performs convolution operation with 256 kernels with the size 2 by 2 by 256 and with stride 1 by 1. Convolution by 1 kernel results in a 20A by 20A by 1 feature map. Convolution by 2 kernels results in a 20A by 20A by 2 feature map. Accordingly, the output is a feature map with the size 20A by 20A by 256. Next, the deconvolution step predicts the masks for all classes. It takes C convolution kernels with the size 1 by 1 by 256 and performs convolution operation to generate a 20A by 20A by C feature map, where C is the number of classes. In our example with 3 classes, C is equal to 3. Each 20A by 20A feature map denotes the mask of a single class. For mask generation, the activation function used by the convolution is sigmoid, This normalizes the output value in the range from 0.0 to 1.0. Then, the resulting feature map is binarized with the 0.5 threshold, and thus produce the binary masks for all object classes. According to the predicted class label from the classification branch. For example, the class is dog. We resize the binary mask of the dog to the predicted rectangular bounding bus. For training mask RCNN, the total loss L on each ROI is defined as the sum of 3 losses, respectively for 3 branches. More specifically, LCLS, LREG, and LMask are the losses defined for classification, regression, and mask branches, respectively. Accordingly, the mask loss is just part of the total loss L. The detailed definition of classification and regression losses can be found in our Faster RCNN YouTube video. We only detail the definition of the mask loss in this video. The mask loss is used to evaluate the difference between the predicted map MPRED and the ground truth map MGT. The selection of the predicted map is according to the ground truth label. In this example, since the ground truth label is dog, we take the second feature map as the predicted map. The ground truth map is obtained by firstly crop the object mask from the ground truth image, and then resize it to the resolution with 20A by 20A. The mask loss is defined as average binary cross entropy BCE loss as expressed in this equation, where n is the total number of points in the map. This term is the BCE loss of a point and is defined as this equation. In this example, n is 20A by 20A, and the sum of BCE losses over all points in the map can be expressed as this equation. This term is the BCE loss of the top left point, and this term is for the next point, and so on. In this video, we introduce the mask RCNN, which is a convolution neural network for instance segmentation. Different from ROI pooling used in the Faster RCNN, mask RCNN uses ROI align for extracting ROI feature map without quantization, and thus significantly improves the segmentation accuracy. The proposed mask branch is in parallel with the other 2 branches and generates masks for every class without competition among classes. Thanks for your listening and have a nice day.